Okay, let's work on this problem. This one is fairly involved. There's a lot to it, and I think it's a great teaching and learning problem. So this is a system we have. It's you've seen a system that looks like this before when we've done force analysis problems. Please keep in mind we're not using force analysis here. We are using energy conservation or energy analysis, as I call it, as our approach. So our givens here are the two masses, the angle of incline, and the coefficient of kinetic friction. So here is just one coefficient, and for both these interfaces, okay? So I know that could potentially be two, but for simplicity, we'll just say that that is the same coefficient that both of the interfaces have. We're asked to determine the tension in the cord here. And another thing we're told about this problem is that we can assume that the system accelerates to the left. Okay, so that kind of gives us something to think about here. Remember that we're going to be using our energy conservation, which tells us that the change in mechanical energy is equal to the sum of the works by our non-conservative forces. And we want to remember that the definition of work is the scalar product of force and displacement here. So it might be good to start by just taking an inventory of what are our non-conservative forces here. So let's do that real quick. Our non-conservative forces that are acting, what are those going to be? Well, friction for sure. Tension, that's also a non-conservative force. Normal force, that's a non-conservative force. And that might be it as far as non-conservative. Remember that the only conservative forces that we have in this class are gravitational force or weight and spring force. There are no springs in this problem, so I'm not thinking about that. But any other force, that means any other force other than weight that appears in the problem is for us a non-conservative force. That's important because that means that we need to consider the work done by these forces when we're calculating the right-hand side of our equation. All right. So what that means is that if I take my energy analysis statement, that'll be the final mechanical energy minus the initial mechanical energy will be equal to the work done by friction plus the work done by tension plus the work done by the normal force. That's just sort of doing one more step there of specificity. Okay, so let's look at our situation here. What we can say here is that, all right, we can assume all we're told here is that the system accelerates to the left. Well, let's go ahead and make the assumption that it's released from rest, and we'll figure out whether that matters or not. But we're not told that it is. But, acceleration can include a zero velocity. Think about the graphs there. So let's just go ahead and say, all right, let's assume we're released from rest and that the system's going to travel. I need to have it travel through some kind of displacement here, right? I got to call that something. I care about that. It's path dependent because we do have friction acting here. So I'm just going to go ahead and call that D. And since that's something I'm introducing, what I do is I introduce it and then I hope that it's going to go away, right? I hope that I'm not introducing something that's like critically important here. Um, what that allows me to do, what's kind of good about defining that D is it allows me to help define, for instance, this mass A. I'm going to need to define how its height changes for the gravitational potential energy term, right? So I'll have to write that somehow, the height change. And now I can write it in terms of D and in terms of phi there. Okay, so let's just start taking inventory here of our energies. And let's say that um, the initial energy is when we release the system from rest. So, where's our energy there? Well, we don't have any kinetic energy. And do we have gravitational potential? Right? So, we can look at it and say, well, I look at mass B. Mass B is just traveling horizontally. In other words, its elevation never changes. And if a body's elevation never changes, then there's not going to be any change in gravitational potential energy. Therefore, gravitational potential energy isn't something that I need to keep track of during this problem. However, mass A, the mass that's on the slope, that's on the incline, its elevation is going to change. So that means its potential energy will change. At release, it's at its highest point there. So I'm just going to call its lowest point, let's say after it's traveled through some distance d. Again, I realize this d is arbitrary, but notice that I need to choose some interval for which to analyze the system. I'm going to say that again. I need to choose some interval for which to analyze the system. So notice as we move on in this class, I'm giving you kind of more and more sophisticated problems, and the sophistication shows up in different ways. And this is one of those ways, right? Where you're not told anything about a distance d, but you should have hopefully by now done enough problems that you can introduce it yourself and be okay with that. So initially, I do have gravitational potential energy of mass A. So I can call that mass A g times whatever the initial height of mass A is. And what I can do is think about this as a triangle right here and say, well, if mass A gets down to the end of this distance d here, so say I'm drawing in a little box of mass A, then it has undergone some height change. So I could draw in a right triangle in order to try to figure out what that height change is going to be. And I know this is the angle phi, and I know the hypotenuse is d. So I know I can write that as m sub a g d sine phi. All right. And again, we're assuming the system is released from rest. So I'll write that in here, that we're assuming v naught equals 0 here. And that's an assumption that we're placing into the system. It's important to note that. Okay, so final energy. Now, what am I calling my final situation? That will be after it has descended through this distance d, right? After the system has gone through some kind of interval that I have to pick here. Well, by then, both the blocks are in motion, right? So I've got 1/2 ma v squared plus 1/2 mb v squared. Now they're tied together by an inelastic cord, so those speeds are going to be the same. Okay, and then what I'm going to do is just set my y equals 0 right here at the lowest point in the interval that I'm studying. So there's no gravitational potential energy at the quote unquote bottom of that interval there. Okay, so that's my initial and final energies. I always start there, right? By trying to wrap my head around the initial and final energies and therefore completing the left-hand side of the energy analysis equation. So keep in mind that this energy analysis equation, that's what's guiding our work as we proceed through these problems using energy analysis as our approach. Okay, so now I need to find the works, and that means that I need to draw free body diagrams, right? So free body diagram for mass A, and then I'll draw a free body diagram for mass B here. They have different forces on them. They're different bodies. I need two diagrams. So if I look at mass A, what do I have there? I've got a normal force. I'm going to switch up my color real quick. I've got a normal force. I'm using a rotated coordinate system, right? I've got a normal force. I've got tension. And then there's also kinetic friction here at the interface. So tension and kinetic friction to the left. And then the surface that's touching it and the cord is touching it. There's nothing else in contact with the block. So apart from that, I just have my weight here. And then I'll go over to mass B. What do I have there? I have a normal force. Now, I don't want to confuse it with the normal force on A, so I better subscript these normal forces, because those quantities are not identical. So we use identical symbols only for identical quantities. If I look at mass B here, now I'm looking at the free body diagram for mass B. I've got tension to the left. I can use the same symbol for tension here. This is a massless pulley. So the tension does not change on either side of that pulley. And then, of course, there's friction at this interface too. So I've got friction, and now I see, oh my gosh, I better use a different symbol here. So I'm going to call this, I'm going to put a superscript B here, and I'll put a superscript A for the frictional force on A. And then, of course, I have the weight of block B. So those are my forces. Since I'm going to be cranking out this scalar product, I want to remind myself of the direction of displacement in both these cases. So I'm just going to float a little arrow here with the displacement direction and for both of these free body diagrams. And that keeps me on track when I'm calculating my scalar product. So notice that when we calculate the scalar product, the sign of the work doesn't depend on your sign convention. And let's say that again. When we calculate the sign of work, when you calculate work, the sign of that work doesn't actually depend on your sign convention at all. It depends on the direction of the two vectors that you're taking the scalar product of, right? It depends on their direction with respect to each other. So it just depends on what is the direction, how do the directions of your force and displacement vectors relate to each other? I know that's a source of confusion or can be for students. And we still emphasize coordinate system. It matters as far as interpreting our, what we're doing. But okay, so let's now go ahead and crank out the works. Um, I'm gonna box up this part here, keep it kind of separate. Okay, so I'm gonna start with the works on mass A here. Let's figure out what those are. So the normal force doesn't do any work, right? It's orthogonal to the displacement. So there's no component of the normal force along the line of displacement, nothing. But I have to look at the other forces. Does tension do work? Sure. So we have work done by tension, and that's going to be equal to magnitude of tension, magnitude of my displacement, times cosine of the angle between the tension and displacement. And notice that for mass A, they point in opposite directions. So that's 180 degrees. That gives me negative TD for work done by tension. And I'm going to superscript this with an A because that's on block A. The work done by friction, again, superscript block A, that's going to be the magnitude of the frictional force, magnitude of my displacement, multiplied by, again, this is a cosine 180 degrees, so this gives me negative force of friction multiplied by D. And I can flesh that out a little bit, right? If I look at my free body diagram for block A, this is again the only place here that I really want you to be thinking as far as Newton's second law goes. Everything else, you should be practicing new skills here, but you can use Newton's second law to define normal force. So if we look at our free body diagram for A, we can see that using Newton's second law, we can see that normal force is equal to the weight of the block times cosine phi because there's no acceleration in the y direction here. Okay, there's no acceleration in the y direction. So the forces along the y axis are equal and opposite. Okay, so in other words, I can rewrite this as negative mu k, the weight of block A, cosine phi, so we're just looking at that component, times d. And then the only other force on block A is the weight, and that's a conservative force. So we are not worrying about that. Okay. Let's look at works on the second block, mass B here. And again, normal force doesn't do any work because it's orthogonal to the displacement. But tension does work. So I'm going to superscript this with a B, and that'll be magnitude of tension, magnitude of displacement times cosine. In this case, it's 0 because displacement and tension are in the same direction. So this gives me a positive TD there. And now I need to find the work done by friction, again for B, which is going to be equal to my frictional force, FKB, times D, and this is cosine 180 degrees. They're in opposite directions, the displacement and the frictional force. So this gives me negative the frictional force on block B multiplied by D. And we can, again, we need to write that in terms of things that we know. So that will be our coefficient times the normal force, which is equal to the weight for block B as it's on a horizontal surface. There are no other vertical forces acting, and there's no acceleration along the Y. So this is just going to be, the normal force is just going to be the weight, and that'll be multiplied by D. Okay, so negative tension there, negative work done by tension, positive work done by tension, equal and opposite. And then I've got my two frictions there. And I wrote those friction works out in terms of givens as well. So we should be feeling pretty good about the right-hand side of our energy equation. You've seen this before. You've seen the tensions that where the work's done by tension sum to 0. That happens when you look at the whole system. So when we look at, because we're looking at this as a system, we're going to sum the work on the works done on both blocks, right? And it's that that causes the tension term to go away. I just want to make that really clear. If I was just looking at one block, if somebody asked me something about this one block, right, then the tension terms wouldn't go away. Okay, so that's a huge hint because what are we being asked for in this problem? Might have to go back. It's been a minute. We're asked to determine the tension in the cord. So now we kind of have to decide what to do because if we're going to sum up all these works all together, that tension term is going to go away, right? So we'll lose it. And sometimes we want that if we're being asked for something else, um, but sometimes we don't. So there are different ways to do this. If you look at the written solution, um, you can kind of get a handle on the different approaches. But what I'm going to do now is I'm just going to pick one of these blocks to look at. I know I need to look at one in isolation because, or by itself, I guess, because I need the tension to be a quote unquote external force in order for it to not equal 0 when I sum up all my works. Okay, so let's say that we're just going to look at block B here. And if you might say, why is she choosing block B? I'm just going to choose block B because it's simpler. That's all. Because it doesn't have any gravitational potential energy changes as it slides along to the left. So it's slightly simpler than block A. So if I just look at block B, so this here, oops, this here is block B only. The initial energy of block B is nothing. It's just sitting there, right? And the final energy for block B is just that it has some kinetic energy. This is mass B. Great. So let's go ahead and put that in our energy equation now using the works on block B. So I'll have 1/2 mb v squared minus 0, always final minus initial. And then I have to kind of go back and remind myself what are the works on block B. So if I look at block B, I remind myself, oh yeah, we had positive work done by tension and negative work done by friction. So mu sub K, mg, m sub B, GD. Let's just go back and make sure I didn't forget anything. Positive work done by tension and negative work done by friction. Okay, so this should allow me to get an expression for tension at least, right? And then we'll see where we go from there. So sometimes it's useful to just get an expression for the thing you want and then see, am I done or am I not done? So TD, if I'm going to solve for that, then that'll be equal to my kinetic energy term plus work done by friction. Right. So this all looks fine except for that speed, which we don't know, right? We don't have an expression for that speed. So there's some different ways to go about this. What you could do is you could look at block A by itself here. We could look at that. We could also look at the system as a whole. And if we look at the system as a whole, the nice thing about doing it that way is that we know that we're going to get rid of the tension and I can just get an expression for the speed, right? Because if I look at block A, what could happen to me? Um, I don't know if it will. I'm not going to go through and do this whole do this all the way out, but what could happen potentially if I use just block A is I could get an expression that when I substitute it in keeps making that tension term go away when I substitute in for my V. So that's possible that I could make that happen. So a safer bet, and you could try that and see what happens. A safer bet would be to look at the entire system. And if you look at the entire system, then you know that your tension is going to go away, right? If I look at my entire system, I can say, right, this is what I was doing on the previous page, where for the entire system, my um, initial energy was, and my final energy were what I wrote in this little box right here, right? So if I'm going to use that and the works that I've come up with, maybe it'll simplify actually a little bit there. So what I would end up with there, my initial energy is just mass A, G, sine phi. And then finally, I have both my kinetic terms. And actually, I'm just going to simplify since the speeds are the same here. And then I can figure that out to do my work. So I'm going to continue that kind of down below here on the left. So I'll have my final minus initial. Oops, there's a D here. Okay, so final minus initial energy equals now the sum of all the works. So if I go back and look at my four works, I can see that these two tensions, the work done by tension, totally goes away. So what I'm left with is the two negative works that are done by kinetic friction. So that's going to be negative mu k ma g cosine phi d minus mu k mbg. That's the normal force for block B, right? Okay, so that's my whole expression here. And the reason I'm just kind of going through this and showing you this is that this is now, there's no tension anywhere in this expression. So I see here that my one unknown quantity in this expression is V, right? The masses are known. Oh, no, D is not known, but I'm just going to really hope to heck that the D goes away, right? I'm probably going to have pretty good luck with that. As I see that if I were to isolate this term over here, that all of my terms are going to contain some D's in there. So I'll probably be okay as far as that goes. So yeah, and if it doesn't go, if my D doesn't go away at this step, then maybe hopefully I can say that it'll go away when I substitute it up here for block B in order to find the tension. Okay, So this kind of gets you started in how to do a problem like this one. And sometimes the solution isn't super direct, right? Sometimes you need to do a couple different moves. But the idea, hopefully what you're learning in this class is you're gaining tools, and you can't always know exactly how to proceed in a problem, but you hopefully have a whole bunch of things that you can try. That's kind of what we're going for here.